So let's say I have a vector here A and a vector here B. A plus B, well, I start with one of them, doesn't matter which one. And now I have a new starting point, and so then I draw the second one, where that's my A and that's B. And so my resultant is from where I begin to where I end. That's the sum of those two vectors. We did that first week or so. A minus B is the same as A plus negative B. And so I start with one of the vectors, I'll probably start with positive one. That's my A. And then plus negative B is going in the opposite direction. Something like that. So there's my resultant. But multiply is a little bit different because I have components here. They're not parallel to each other. The wrong one down. So I could break up A into two parts to it. I have the part that's parallel to B and the part that is perpendicular to B. And so when you're multiplying, the key thing is, are you going to multiply the parallel parts or the perpendicular parts? If you're multiplying parallel parts, you're doing the dot product. If you do the perpendicular parts, you're doing what's known as a cross product. And if you think about a cross, they are perpendicular line segments. Cross products go with perpendicular. But this cares about parallel. I want to multiply B, the length of B times a part that is parallel to it. So if my angle here is theta, the part that is parallel to B would be A times the cosine of theta. So A, one of these will work well. So A dot B, the reason why it's called a dot product is we use a dot here. You can't just use any old multiplication symbol. It's going to be the part of A parallel to B, which is A cosine theta, times B. Or, as typically written, A B cosine theta.
Isn't that a rule for like AB cosine of theta? Isn't that like some sort of like cosine rule or something?
No, there is a law of cosines has a magnitude cosine theta in it. That might be what you're thinking of. I don't know.
Probably. Where are we gonna use this? Like, this kind of makes sense. I just don't know what context we're gonna use it.
And deriving the fourth one.
Okay.
It also shows up when you talk about working energy. Dot products show up.
Wait, so why did you start like doing the vector A minus vector B equals A plus minus B? I'm kind of lost on that.
Whenever you subtract, what you're doing is you're adding a negative. So 4 minus 3 is 4 plus negative 3. Those are the same thing.
So that's just what we were trying to show.
Yeah. Just connecting it with the stuff that we've done already with other things. I was trying to remember if we'd actually done a subtraction problem with vectors before, but now we have.
When you're subtracting the B vector, where you've got like A minus B, how do you know which direction the B vector is gonna go in? Because when you first started drawing it, I thought
Like, B was gonna go, wait. I thought B was just gonna go in opposite direction. That
All right, so
doesn't make sense.
B goes that way,
Right,
but negative B
would go that way.
is the opposite.
So if you've got one that like goes that way, it'll go that way.
Yeah, the negative just means other way.
Okay, never
So
mind, that makes sense.
we did the same thing with I hat. I picked the direction of I hat. The opposite way was negative I hat. Lisa?
Wait, so the resultant is, like, it's gonna be A times whatever is parallel to A?
Oh, over here with the product?
Yeah.
When you're doing a dot product, you want to multiply parallel components. And so, if I have a vector, draw it a little bit differently. So I have some vector A here, and I have some vector B here, where B will just make B horizontal. When I'm doing a dot product, I need to multiply the parts that are parallel. I break A up into its components, into perpendicular components. In other words, I'm creating a right triangle where one of the sides is parallel to B. This, when you do a dot product, I'm gonna multiply that length times whatever that length is.
Okay.
Then,
Is the green line TR?
It's the sign for resultant.
The one like AB on the triangle?
The like.
The resultant.
The resultant symbol.
R?
that's my double print R. That's the one time I use double print to represent a vector. For whatever reason, probably some childhood scar. All right, any other questions right now?
So basically, our solutions, which is the result, we're just finding legs of a triangle, sort of.
I mean,
First.
ultimately, it comes down to, I'm doing a dot product between vectors. It's the product of the magnitudes times the cosine of the angle between them when they're tail to tail.
When you're doing dot product, you're not looking for the resultant.
It's not officially a resultant if it's a product.
Right.
Yeah, we're,
You're just calling it something different.
yeah, it's the scalar product. I do note that they start out as vectors, but they don't end as a vector. This is a scalar here,
Okay.
Why is that?
because the powers that be said so. That's just the nature of dot products.
Okay.
How would you choose a direction? Anyway, I got things in not different directions here. What would you choose as the direction of the product?
Yeah. Just like.
Now, with cross products, we actually do have a way of creating a product, a direction for that, but that's later. Sort of dangle that out there. The way my elementary school teacher talked about finding area under curve by adding up a whole lot of rectangles. No idea what she was talking about until I took calculus, and I thought, oh, that's what she's been talking about all those, back in fourth grade.
I was gonna say that those last problem, we're actually finding area, right?
Yeah,
Okay.
but it gets a lot trickier if, you're dealing with a curve.
Right. Actually did touch on something similar to that in statistics.
Ah, okay. So they decided to introduce some math into statistics? Yeah, that was a slam against statistics people. I was talking to the camera. All right, so let's take a look at this one more time. So I have some vector A here and some vector B here. I broke A up into its components. I don't have to. I could break B up into its components. So I know part of B is parallel to A, and then part of it is perpendicular. See if I can actually draw that a little bit better. And if this angle between them is theta, this small little side right here is just going to be the hypotenuse, the magnitude of B, times the cosine of theta. And so my dot product of A dot B is just A times B cosine theta. Or, as more traditionally written, AB cosine theta. So let's actually stick some numbers in here. I have some vector A, which is, let's say, 5 newtons, 33 degrees, and then some vector B, which is 4 meters, 57 degrees. A dot B, it's supposed to be a dot there, is just gonna be the magnitude of A times the magnitude of B times the cosine of the angle between them.
So average 33.
Not average difference.
Okay.
Because one of them is at a 33-degree angle, that's 33 degrees,
Okay, yeah, so you subtract.
and the other one's at 57, so we want the difference.
Okay.
And what is this, by the way?
What would the unit be though? Cause you got like newtons and meters.
Is it, it's like 8.48 something.
Something's off there.
5 times 4 is 20, 20
Yeah.
cosine of 24.
Yeah. 44 degrees.
Yeah. Hold on. Alright.
Yeah, what?
18.27.
All right, so let's talk about units. What would the units be?
No idea.
Meters.
Somebody just said it, I think.
Newton meter.
Yeah, it's just newtons, meters. Or newton meters.
Is that a dot in between?
That's a dot in between.
Okay.
Now, the dot in between is not the same as this dot over here. This is just, I'm multiplying newtons times meters here. The capital N does not have any meaning in terms of prefixes. You know, if you have a K in front, it means kilo. If I have a lowercase c in front, it means centa. Capital N, I don't think has any prefix meaning to it. So if you drop the dot like that, it's not officially an issue. It is an issue if you decide to write it as a meter newton. Now, typically it is written in newton meters. The capital N comes first, but the difference is that is a meter newton. That is a millinewton. So the dot typically you put in there just to make sure that it's clear that you're multiplying units as opposed to,
Millinewton,
yeah, and also, some people write their capital N's like just a large lowercase n. In that case, it might look like nanometers if you leave the dot out.
Yeah, are dot products gonna be on our first test, or is this just to help us, understand the,
Primarily to help you understand this in terms of, when have I typically, like, dot products we hit heavily in chapter, I think 7. That's where we officially start working with them. One other thing, if this is actually a force that is pushing an object that goes 4 meters, and the force, so I have a box, and I'm pushing on it at an angle here of 24 degrees, 5 newtons, and the box slides 4 meters. In that context, the newton meter is a joule. There is another, what's called a derived unit called a joule.
That's an electricity thing.
There too, when talking about energy or work. In chapter 9, I think it is, we'll get to a newton meter, which is not a joule, which is an unfortunate thing, but it's just the way it is. So if I do a cross product between them, I would still have a newton meter as my unit, but it's not joule.
Are you saying meters, newtons? Meters, newton is the same as newton meter?
Yeah. It's just not traditionally said that way.
I was gonna say, I'm very familiar with newton meter, meter newtons.
Yeah, it's like you say foot pounds instead of pound feet.
Right. Say it at work, they'll think I'm dyslexic.
That could be too.
Meters, newton.
All right, so let's take a look at, since we're multiplying parallel here, I gave you a nice simple example here. You're in polar, I gave you a polar form, so you already have the magnitudes, you just subtract to figure out what the angle is, plug and chug. What happens if you're rectangular? Then,
To get the cos 24, do you have to always like subtract the 57, like the bigger number from the less number?
no, you could have done 33 degrees minus 57 degrees. The cosine is an even function. So the cosine of 33 degrees minus 57 degrees equals the cosine of 57 degrees minus 33 degrees. Cosine, you can do that either way. One other thing to point out here, commutative property holds. Doesn't matter the order in which you will do a dot product, unlike cross products.
Right. Yeah, that's all that really is.
Yeah.
It's time, so it's either way.
Now, suppose A is equal to 5 I hat, we'll drop the units here, 5 I hat plus 3 J hat, and B is 4 I hat minus 2 J hat. Let's do this the long way. The answer's 14, by the way. But the long way, 5 I hat plus 3 J hat, dot product, 4 I hat minus 2 J hat. And then let's FOIL. First, so I got 20 I hat dot I hat plus outer -10 I hat dot J hat. Somebody said something, I missed it, I'm sorry.
I was just saying what you were doing.
Okay. Next.
12 I hat dot J hat.
Now, J hat comes first here, and then I hat, but commutative property holds, absolutely nothing wrong with that.
Minus 6 J hat times J hat, or dot J hat.
All right, so I have these I hat, J hat, I got these dot products between unit vectors. Well, let's think about what that actually means. Let's not forget our formula here. So I hat dot I hat. Well, what's the magnitude of I hat?
1.
Yep, 1. Times 1 times the cosine of the angle between them.
0.
0. Degrees over radians, whichever way you like. And what does that equal to? I hat dot J hat. I have 1 times 1 times the cosine of, what's the angle between I hat and J hat?
0.
0.
Ooh,
90.
somebody said it.
90.
I need units this time.
5 degrees.
Why is it 90? Because I hat, aren't they like interchangeable?
No, they're perpendicular. Whenever I do it, we have I hat, J hat, or they're I hat, J hat, K hat are all perpendicular to each other.
Okay, makes sense.
Thus the rectangular coordinate system.
So if you did like I hat and K hat, would it be 180?
No, K hat would be, it's still 90 degrees from the other two.
Okay.
So anyway, what is 1 times the cosine of 90 degrees?
0.
If you don't believe it, try it. Just make sure you're in degrees and not radians. So what this means is that all the terms that are mixing I hats and J hats go away, and I'm left with 20 times 1 minus 6 times 1, which is 14. So I could have just done this a much shorter way with a rectangular form and just multiply the like terms. And multiply the I hats together, multiply the J hats together, add. So 5, I'm stuck in right there. Surely there are other numbers besides this one. 6 I hat minus 7 j hat, dot product, negative 2 I hat, plus 3 j hat, minus 4 k hat. And the answer is?
Negative 37.
Did I do one math wrong?
No.
Not negative 37. Multiply the components that are the same direction. So you multiply the I hats together, what do you get?
Negative 12.
Multiply the j hats together, you get.
Negative 21.
Multiply the k hats together, and you get
Negative 4. Or just, oh, is it a 0?
0. I don't have to write plus 0 k hat here, but it's, I can write plus 0 anything.
So it's just negative 33.
Yep.
Oh, okay. I subtracted the 4.
Yeah, if I had plus 1 k hat, then yes,
Okay.
but I don't have a k hat over here, so that just gets ignored in the dot product. It's parallel to nothing.
So we wouldn't. Okay, never mind. I was thinking about it, cause I hat and k hat, or I hat times k hat is just 0,
Correct.
cause it's the same as I hat and j hat.
Absolutely.
Okay, thank you.
Can you do this, like this example thing one more time? Just so I can like, know I
Oh,
can do it?
do we write it out the long way? Is that what you're suggesting, or just?
Okay. Or like, not the same, like different numbers, like doing what we just
Oh,
did.
oh, oh,
different
oh.
numbers.